Hello guys, welcome to Fire Racer Workshop, and in today's video we're gonna be starting out with the experiment series on logic gates. Now there are particularly two experiments that will be covered in logic gates in our second semester. So the first experiment, the aim for the first experiment is the verification of the basic logic gates. So there are 6 basic logic gates that we're gonna be covering in this particular video on OrCAD software. I'm also going to be making a video on the TinkerCad software, but you have to just stick around for that video because it's just going to take a bit more time, because I just want to get over with the OrCAD software for the second semester first of all. So guys, if you don't know me, I'm covering all the experiments that are present in the second semester of our BTECH syllabus for the IPU University. We have already covered the experiments. First, to plot the VI characteristics of a semiconductor diode. Second, to study the reverse characteristics of a ZENER diode. Third, to study the half wave rectifier. Fourth, to study the center tap rectifier. Fifth, to study the bridge rectifier. And now we're gonna be starting with the logic gates. And these experiments are gonna be the most simple experiments that you're gonna be performing. So let's just get started with the video. There's something that I need to tell you. These particular experiments, so first of all, this is what our circuit is gonna look like for today's experiment. So this is one of the logic gates. This is one of the first logic gates that we're gonna be covering, and this is a simulation for that logic gate. I will also make this video on TinkerCad so that the students have a clear understanding of the logic gates, because I just don't want any students to face any difficulties when they have just completed their engineering. If you want to learn more about the logic gates, I have provided some really great videos in the description box of this video, so do check them out. Please check the description of the video. It's just really important because I just do link a lot of stuff in the description that's gonna be really helpful to you. So without wasting any more time, let's just get started. First of all, I'm gonna be opening up my OrCAD software. So over here I have the OrCAD software. I'm just click on it. Okay, so we're gonna go with the OrCAD PCB Design Professional with PSpice. So I'm not just going to be covering each and every basics in this experiment, as I have already made a lot of videos on OrCAD. So I'm just going to straight away go with the experiment. Let's just open up a new project, create a new project. Now we're going to name it as logic gates. Logic underscore gate underscore trial underscore, let's just name it trial 1. So already the location has been selected properly for these particular circuits that are like that I'm just gonna be saving. So you have to just select your location here wherever you wanna save the circuit. So it's just really important that you just keep it in one folder only, because it's just like keep all the stuff managed. So I've just like created this particular folder in which I just save all the experiments that I perform. I'm just gonna hit OK, create a blank project, hit OK. Now let's just first of all cross the startup page. Now what you're gonna do is we're gonna import first of all our logic gate IC. Okay, so our logic gate IC for this particular experiment is, let's just click on P to open up the part window. So the logic gate IC that we're gonna be using is 74LS00. So this is gonna be our logic gate IC that we are gonna be using for this particular experiment. Now you have to make sure that you just pick up the right IC. Over here you can see I have got many options for this IC. I'm particularly got 3 options for this particular IC. So I'm just gonna click on the IC that shows me the PSpice symbol over here. So it means that a simulation profile etc. is available for the PSpice to simulate this particular logic gate. So over here you can see this particular IC has a simulation profile. This one has it, and this one also this one doesn't has it. So this is kind of a design cache kind of thing. So we're gonna go with we can just go with any of these. So I'm just gonna go with this one. I'm just gonna go with this one. Only this one has it. I'm sorry, only this one has it. So I'm just gonna double click on it, just import it. Okay, cross it out and zoom it in a bit so you people can see it clearly. Now we're going to be importing our digital sources to simulate this particular IC. So these particular sources are going to act as the input for the IC. So what you're going to do is you're just going to find the source library in this particular section that is called the libraries. So search for the source library. It's gonna be somewhere over here. You can see we have just found the source library. Just click on the digital clock, double tap on it, and this is gonna be your source. So press R to rotate it. We're gonna place it here. Another one, we're just gonna place it over here, and let's just make the parameters disappear for a while. So because we need to just run the wires from here, so I just don't need the parameters to just come in between and these to be like really hard to read. So now we need something to detect the output of the IC. So what you're gonna do is you're just gonna click on this particular symbol right here. This is called the place port, and what you're gonna do is in the first section only you are gonna find the place port. So port both -L CAPSYM. So you can import any of the first 4 or 5. So these are just going to work the same. These are just going to detect the input. So the difference is in the shape and where they are detecting the input. So this is going to detect it at the left side, and for this particular one it's just going to detect it at the right side. So let's just leave it, and I'm just going to import this one. So let's just hit OK, and I'm just going to place it over here. Let's just wire everything up. The wiring is complete, and let's just set the parameters for these things. So you can see over here, this is called the off time. So first parameter is called the off time. So it is a time for which the digital simulation, this particular digital source is gonna stay off. So it's just gonna provide us with a 0 volt, 5 volt, 0 volt, 5 volt. So it's just gonna provide us with a square wave. So this is the off time of this particular source. So this is set to 0.25 microsecond, but we're gonna just change it. We just want it in the millisecond range. So let's just change it to 5 milliseconds. Actually, yeah. So similarly for the on time, we are just gonna change it to 5 millisecond as well, because we want the duty cycle of our output to remain 50%. So the time for which the source is going to be on is going to be equal to the time for which the source is going to be off. Let's just hit OK. You just don't need to set any delays, so you just want it to start instantaneously as we start the simulation, and start value is going to be 0 volts. So it's just going to start with a value of 0 volts. Okay, so let's just set the parameters for this one as well. So this is not going to be the 5 millisecond as the previous one. So this is going to be the 10 millisecond. And why we are doing it, I'm just going to tell you in a while. You just set it to 10 milliseconds as well. Okay, so we are all set. We just don't need to set any delays, or we just don't need to change any of the values. So our circuit is ready to be simulated. Open up PSpice, create a new simulation profile. Name the profile as trial. I'm probably at the trial number 10 by now. So let's just create it. Now simulation window is just gonna pop up. So over here you can see we just don't need to perform any of these. So we're not gonna perform DC sweep, neither we're gonna perform AC sweep, or neither we're gonna perform the bias point analysis. So we're just gonna click on analysis type as time domain, and the runtime is gonna be 20 millisecond, and the maximum step size is gonna be 0.1 millisecond. Be careful to change this parameter as well, because this way your graph will look much neater. Okay, so there's nothing else that we need to change. Let's just click on apply, click on OK, and now we're just gonna run the simulation. It will take some time to run the simulation. Okay, simulation has been complete. Let's just go to trace option. You don't need to change anything in the plot section, so just go to trace option, add trace, and DSTM1 and DSTM2. These both are the inputs. So the DSTM1, so this particular input, this is the one that is having a longer time period, and DSTM2 is having a shorter time period. Okay, so let's just add these two, and now you see why we have chosen the these particular, the on time and the off time, as 10 milliseconds and 5 milliseconds respectively, because at this particular stage this is at the low position, and this particular output is just going to switch from low to high. So this is just going to give us the two conditions in our truth table. Let me show you the truth table once. So this is the truth table for the IC. So it's just going to give us the first two conditions, that is the low low and the low high. And after that, when it just switches to high, this one will switch to low. Okay, so this is switched to high and this is switched to low, and then it always, like, it just remains high for the entire life ahead of it, and this will just stay, first of all it will stay low and then it will stay high. So for example, now in this particular case we are just getting a condition of high low and high high. Okay, you can see in the data sheet as well. So this is the high low and high high. So all the four parameters are getting tested by this method. Now let's just add the trace for the output. So our output is PORT-BOTHL. Let's just add it, hit OK, and you can see over here for the first three conditions, that is the low low, low high, high low. Okay, so the output is staying at 5 volts, and when the condition is like high high, then the output is dropping to 0 volts. Okay, so this is how this IC is simulated. Now what we need to do, so let's just move on to the next IC. So the truth table for this particular IC has been verified. So the truth table has been verified. Okay, let's just move on to the next IC, that is the DM74LS02. So this is a NOR gate IC. Okay, so it's a quad channel NOR gate IC, and over here I'm just going to show you the package of this IC. So this is going to be a similar package that we had in the previous one as well. So the truth table for this particular IC is shown over here. So it's just going to be, so the output is just going to be high if both the inputs are at low. Okay, otherwise it will always stay low. So you're just going to remember this. So this is the truth table for this particular IC. Okay, let's just simulate this IC. So again, you can see this is a quad channel, this is a quad NOR gate IC. So you can see these are 4 NOR gates that are present within the IC. Okay, so these A1, this is the input, A1 is the input, and Y1 is the output. Okay, so let's just simulate this IC. So what we need to do is, in the PSpice, in the OrCAD, what you need to do is just delete this IC, and again we need to select all the libraries. Just tap on the first library, press shift, tap on the second library, all libraries will be selected. So let's just type in the name of the IC. Okay, so the name of the IC is, so it is the 74LS02. So let's just type in the name of the IC, 74LS02. So this particular IC, we're just gonna attach it over here, and we are all done. Let's just simulate a circuit. It's just showing me some warnings. I got it, what happened. So this particular IC has no simulation profile available for it. So actually I forgot to check which IC had the simulation profile. So this particular IC does not have the simulation profile. It's just a design cache that we can just use in our designs. This particular IC has a simulation profile. You can see over here it's just showing me the model. So it has a PSpice model available for, PSpice has a model available for this particular IC. Let's just import it over here, remove this green warning, and then simulate the circuit again. Okay, so let's just add the trace. So I'm just going to add all these traces at a single time. So first two are the inputs and the second one is the output. So at the condition of 0 0, so the IC, the output of the IC is high. At the condition of low high or the 0 1, the condition, the state of the IC is gonna be 0, At the condition of 1 0, the condition of the output of the IC is going to be 0, and at the condition of 1 1, the output of the IC is going to be 0. So this is exactly matching up with the truth table of the IC. So here you can see the truth table, so it's just exactly matching up, so it is verified. So let's just move on to the next IC. So this is a hex inverter. This is a hex inverting gates. So this IC, the name of this IC is 74LS04. So this particular IC has 6 hex inverters in it. So what is hex inverter is just pretty clear with the name itself, that it just inverts the signal that it receives at its input. For example, if it's receiving a signal of 1 volt, sorry, not 1 volt, actually it's just receiving a 1 as a bit, like I'm just talking binary. If it's receiving a 1, at the output it will just show us 0. If it's receiving a 0, then it will just show us a 1. It just inverts your signal. Like for example, the high will become low and the low will become high. So at the input, if you give a high, the output is going to be low, and if in the input you're just going to give it low, the output is going to become high. So I also have one of these IC just laying around in my lab, so I'm just going to show you a quick video of this particular IC. Over here guys, I have a hex inverter IC. So this particular IC is a hex inverter, so I have just 2 hex inverter ICs. So over here you can see this is the package. This is how the package looks like. This is a through-hole package. However, the IC that we are using is not available in the through-hole one, so it's only available in the SMD one. So it is a dual line through-hole, and we can also use our inbuilt logic analyzer in our oscilloscope. So this is my Hantek oscilloscope. So this has a 16 channel logic analyzer that's built into it. So we can use this logic analyzer to just analyze the behavior of our logic gates as well. So this is just, so I'll soon upload a video in which I'll show the output of each and every logic gate using my oscilloscope, my Hantek oscilloscope, and with the help of its inbuilt logic analyzer. So stay tuned for that video. Now getting back to the PC. So this has 6 inverters that are inbuilt into the IC. This 1, 2, 3, 4, 5, and 6. These are the 6 inverters that are built into this IC. So again, the package of the IC is going to be similar. So all the ICs have a similar package that we are going to be using today. So this is the package. So this IC is also again available only in the SMD format. So let's just simulate it. So in the PSpice, let's just delete this and we are going to remove one of our sources. Okay, delete one of our sources, and let's just import the hex inverter. I'm just going to also delete the wires as well. So the IC number was 74LS02. By the way, the LS name reminds me of the LS engine in the Corvette. So I hope you know what an LS engine is. So these engines were used in the Corvette. So anyways, so this we're just going to import this one. At the first search result that I'm getting has no simulation profile available for it. So we're going to import the second one. Just double tap on it to import it. Just attach it to the output first. Click W and just attach it to the input and just simulate this circuit. Okay, so in the trace, add trace, input and output. So this is our input. So you can see when the input is low, the output is gonna be high. So you can just consider it to be 0 and 1. So if the input is 0, the output is gonna be 1. If the input is gonna be 1, the output is gonna be 0. So it's just inverting the signal. So truth table for this particular IC has also been verified. So you can see all the inputs are just matching up. So this is the fourth IC that we're gonna be simulating today. So this particular IC, so this is a quad channel AND gate IC. So these are the AND gates that are present in the IC. So there are, in particular, there are 4 AND gates that are present. So 1, 2, 3, 4, and this is the truth table for the IC. Now you can see that if both the inputs are at high, then only the output is gonna be high. Otherwise, it's always gonna remain at 0. Okay, or low, whatever you call it. So again, low signifies the 0 volt or 0 in binary, and high signifies 5 volts or 1 in binary. So this is the truth table for the IC. Let's just replace this IC in the PSpice. Let's just delete this IC. Now what I did was to just copy paste the source, the digital source that I've just like deleted. So I'm just gonna add it back. You see, I'm a bit clever in saving time. And I just forgot to tell you this thing also. So I'm sorry if I just wasted your time. So let's just import the IC. So it was 74LS08. So again, the first search result is like the simulation profile for this first result is not available. So we're gonna go with the second one. Over here you can see both the icons are available. So let's just add it. Tap on W for enabling us to do the wiring. Wiring complete. Let's just simulate this. Okay. In the trace window, add trace, input 1, input 2, and output. Now you can see if the input is at 0, 0, the output is gonna be at 0. If the input is at 0, 1, the output is gonna be 0. If the input is gonna be 1, 0, the output is gonna be 0. But if the input is 1, 1, then only the output is gonna be 1. So this is how the truth table for this particular IC has been verified. So this is verified, or KDS, kill death slaughtered. Okay, let's just move on to the next IC. So this is a quad channel OR gate IC. So this particular IC has 4 OR gates. So gate number 1, gate number 2, gate number 3, and gate number 4. By the way, all these 4 OR gates are independent of one another. Okay, so be careful of that. So these have no relation other than the supply voltage. So this is the truth table for the IC. And again, the package for this particular IC is going to be similar. So this is a package for this particular IC. Again, it's an SMD package. So it just can't be used on the breadboards or in a perf board. So for this particular IC, what you have is the output is going to be low if both the inputs are low. Otherwise, it's just going to stay high. Okay. So this is the truth table. Let's just verify it. Move on to the OrCAD. Okay. So the IC number for this particular one is L74LS32. Okay, so let's just type in 32. So again, the first result has no simulation profile. Go with second result. In your particular case, that might be different. So don't just copy paste me entirely, because you might not have imported this particular library in which the simulation profile is not available. So please make sure that both these icons are like popping up on your screen. Otherwise, just select the next IC. Just make sure that the first number of the IC is same. So be careful of that. Let's just simulate this. Again, in our trace option, add trace. Both these traces will be added. Add this one. Okay. So here we go. Now, if the input, for example, now if the first input is gonna be at 0, second input is going to be at 0, the output is going to be at 0. Okay, so this is the first primary condition that was a bit different for the output. So at 0, 0, the output is going to be at 0. At 0, 1, the output is going to be 1. At 1, 0, the output is going to be 1. And at 1, 1, the output is going to be at 1. So the truth table for this particular IC has also been verified. So this has been verified. So KDS again, KDS. Now this particular experiment just takes a lot, like this experiment is just like real quick if we perform it on TinkerCad, because you can just perform all the logic gate experiment at once. Now I'm just going to show you the trick for that. So you might have already guessed it by when I just showed you the screenshots of or the video of the experiment that I've performed on the TinkerCad. So this is just like really easy to do on the TinkerCad. So the next IC for today is, so this is also going to be our last IC. So this is a quad channel OR gate IC. So the IC number is 74LS86. So these are 4 OR gates. Okay, so this is an OR gate IC. By the way, I'm just referring to the data sheets of this IC, and all the data sheets will be linked in the description box below. So do check out the description. So this is the truth table for the IC. Okay, so if the output is gonna be low if both the inputs are low, and the output is gonna be low if both the inputs are high. So if the inputs are same, then the output is gonna be low. For example, if the output is if the input is low and low, the output is gonna be low. If the input is gonna be high and high, the output is gonna be low. But if the inputs are different from one another, for example, if low or high condition occurs, then the output is gonna be high. So this is how you can just remember the truth table for this particular IC. So let's just delete this IC first of all, and this was the 86. So the first number for all the ICs that we have used today is same, so you're just gonna change the last number, so that's a 86 instead of 3286. So we're just gonna choose simulation profile is not available for many of these ICs, so only the simulation profile is available for the 74LS686A. so let's just double tap on it. So simulation profile is available, so you can see over here. So the A is basically a submodel of this IC, so we're just gonna make sure that the logic gate is the same. So the symbol for this logic gate is this. So yeah, of course it's just the same logic gate. So let's just simulate it again using PSpice. So let's just add the trace, and this is going to be the last IC of the day. Now you can see at the low, at the 0 0, if the input is going to be 0 and 0, the output is going to be 0. If the input is going to be 0 and 1, the output is going to be high because the inputs are different from one another. So one is 0, one is 1, and so the output is going to be 1. If the input is 1 and then 0, so the output is going to be 1. And if the input is 1 1, then the output is going to be 0. So this is how the truth table for this particular IC has also been verified. Okay, so you have just verified the truth table for all the ICs. So all the 6 ICs have been complete, and with this the experiment has also been complete. I hope you like this video. If you have any doubt, just go to the comment section down below and just ask me. You can also DM me on my personal WhatsApp number. So my WhatsApp number is by the way given in the description of my channel, so you can just check it out, and you can just personally message me if you have any doubts, so I will just help you out. So that's all for today guys. I hope you like this video. Don't forget to subscribe to my channel, like this video, and share it with your friends, because this video might just help your friend in getting the practical in a bit logical way. So thank you all for watching.